Let's then continue with what we were talking about last time, which was shear stress in riveted or bolted connection. And if you recall, we said that the force, the shear force in the bolt, comes from two sources. One is the direct application of the load itself, which is divided amongst the rivets equally, and the other comes from any moment that that force may create. So we had what we called the primary load. F is the external load. Primary load for each bolt is equal to that external load divided by the number of bolts. Straight division. Now, there may or may not be a moment generated as well. For example, if the connection is under straight tension, no bending moment, then there is no bending moment. This is it. That's all you get. However, if there is a bending moment, then we get a secondary load called F double prime, which we found out last time. To be related to the moment like that. And we said that the farther the bolt or the rivet is from the centroid, and this is all about the centroid, the farther it is, the larger the secondary force that it carries from the application of the moment. So let's take a look at an example problem and see how you would solve a problem like that. This problem is not in your handout, so please draw the picture and write it down. And this is the view from the side. Like that. The dimensions here are 2.5 inches. 2.5 inches. We're taking these dimensions or the distance between the bolt center and the end of the plate, at least 3 to 4 bolt diameters, to make sure that the type of failures that we were talking about, like splitting of the plate, does not occur. 2.5 inches. These are 1/2 inch diameter bolts. I will write that in a second. And this force from the first bolt here, 7 inches. One 1/2 inch diameter bolts or rivets, whichever. Find shear stress in each bolt. Now the bolts, let's just name them A, B, and C. So when you have these bolts in problems such as this, you need to find the centroid of the bolts. So we're looking at something like this. With those dimensions that are given, let me make that a little bit larger. Those dimensions that are given, you have one here. So you have a triangle here like this, connecting the center of bolts. All of them 1/2 inch diameter. The centroid of that, you can either do your summation of xi, yi, and all of that, or say this is a triangle and the centroid lies where the medians meet. That's the centroid. Those are the medians. I'll let you do the trig on this to find that this distance from here to here is 1.67 inches. And of course that makes, you also need these 1.5 inches. The top two are symmetric. Any questions? Okay. Now, that's the centroid over here. We transfer this force given as F equals 2,000 pounds. The force that's applied down there at 7 inches, 2,000 pounds. So we transfer this force from here to the centroid of the bolts, and we get a force like this, F, and a bending moment, M. That bending moment we can calculate as M equals 7 plus 1.67 times 2,000, 17,340 pound-inch. Our primary load, F prime, comes from 2,000 divided by 3, 667 pounds. Our secondary comes from this equation. And you have to calculate it for each bolt, because the distance Ri is different for different bolts. So for bolt A, it's the moment, which is 17,340, multiplied by the distance from the centroid to the center of that bolt, 1.67, divided by the summation of Ri squared, 1.67 squared plus 2 times 1.5 squared. I guess I didn't need the parentheses after all. Do you have any questions? This comes out to be equal to 3,973 pounds. For B and C, because of symmetry about that axis, the distance from the centroid to B and the centroid to C are equal. Therefore, the secondary force for B and C is the same. So we say F double prime B equals F double prime C equals the moment, 17,340 multiplied by 1.5 divided by 1.67 squared plus 2 times 1.5 squared. And that comes out to be equal to 3,568. Yeah, 3,568 pounds. Any questions? Okay. Now, remember that these forces that we have found, secondary and primary, are vectors. And in order to add them, you must do so vectorially. Also remember that we said that the moment here will be resisted by these forces multiplied by the respective distance from the centroid, and then added up. The farther a bolt is from the centroid, the more force it carries associated with the applied moment. The farther it is, the more force it carries. Everybody okay with that? We talked about that last time. So when you look at the forces that are applied here, they must be perpendicular to the line joining the center of that bolt and the centroid. That, by the way, is not a free body diagram. It's the effect of the moment on the forces. So which one of these rivets or bolts is going to carry the most load? A, because both the force, the primary force, coming from this 2,000 pound, that's in that direction, and the secondary force, coming from the moment, they're both in the x direction, they add. Therefore, for A, we have Fa is equal to Fa prime plus Fa double prime. We have Fa prime. This is the same for all of them, Fa prime. Fa prime, Fp prime, Fc prime, all the same. So 667 plus 3973, that's equal to 4,640. Insofar as the other two are concerned, for example, for B, We have 667 here. And then we have this. This is F prime. This is FB prime. FB double prime, sorry. Which is equal to 3,568. You have to add those vectorially. That's FB. You have to find this angle here by taking from that triangle. This angle comes out to be 33.75 degrees. I'll let you do that. And then obviously the force FB is not going to be as large as FA. FB and FB is 3,245 pounds. Taking a look at C, we have a force like this, 2,000 pounds. And then the other one is like this. Again, that angle is 33.75. Again, you must add those two to get FC. And of course, you find that the two are equal. So FC is equal to FB. $3,245. To find the shear stress, you divide each of these by the cross-sectional area of the bolt. So tau A, oh, let me write black. .4640 divided by pi d squared over 4. Half-inch diameter bolts, 16,530 psi. And for B and C, did I calculate the shear stress here? Oh, sorry, I gave you the wrong answer here. Sorry about that. The answer is 23,600. Then tau B equals tau C equals 3,245 divided by pi d squared over 4. That will give you 16,530 psi. Any questions? Yes.
Is the horizontal force for C supposed to be 667 instead of
660. Oh, yes, 667. Thank you. Yes, thank you for that. Same as the other two. The answer is still correct, however. Any other questions? How do you find the bearing stress? Let's say for A is equal to what? Remember bearing stress? I drew a sketch for you. Is equal to the load divided by this area, in fact, depending on, if we assume that these two plates have the same thickness, this area. To do that, you need the thickness of the plate. We have the thickness of the plate is not given. But if that's given, just load divided by the thickness of the plate divided by the diameter of the bolt. It's the cross-section of the bolt through its middle equal to bolt diameter times the thickness of the plate. Any questions? All right. We will now take a quick look at shafts, although it's a whole chapter in your book. A lot of it is related to the placement of various components. Shafts, as you know, are load-bearing members on which we secure gears, sprockets, chains, bearings, what have you. And they are used to transmit power. And in order to transmit power, they must have a rotational speed. We have different shafts, those that carry basically static load, and they do not rotate. They're called axles. For example, if you imagine a rear-wheel driven car, rear drive, then the axle that connects the wheel or the tire to the body of the shaft, that axle itself may be stationary. It doesn't have to rotate with the tire. The tire can rotate on a bearing, if you wish. That's the type of thing we call an axle, as opposed to a shaft that rotates. If it rotates, of course, then it becomes a shaft. So mostly the first part of this chapter, as you read in the book, deals with the location of various components. The shaft is usually the last component to be designed. So you design where your gears, for example, are going to fall. Then you design the shaft to install those gears on, or pulley systems here. When we do this, we have to secure these, a gear, a sprocket, a bearing. You have to secure these on the shaft. We can do it via shoulders, as you can see here. We can locate it via shoulders or via a keyhole and a key. Or if it is not carrying too much torque, a set screw may even do. But any one of those, of course, requires a stress analysis. Unfortunately, we will not be doing that in this course. We won't take a look at various connections such as keys and splines and all of those. You have done a little bit of that in ME 233. But here, what I'm going to emphasize really is the stress analysis of shafts. And most of that we have also done. So what you will see today are basically equations that are related to the equations we did when we did fatigue in general, and also failure theories, both static and, of course, and dynamic. Couple of words about these. When you read about these, they sometimes, when locating this, the stress flow, if it comes across here and sharply goes out, gives you a large stress concentration factor. Sometimes you make an undercut to reduce that stress concentration factor. Sometimes you do this to redirect the line of flow of stresses so that they don't come in here and give you a sharp change in the direction. These are called stress line. Just like they mimic the flow of fluids through pipes, exactly. And the stress concentration location or the change of geometry is akin to a part of the pipe that may interfere with the flow of a liquid or gas for that matter. So that's basically what most of this chapter is about. I would like to say, I would like to talk about this for a couple of seconds. Most shafts are loaded as you see. If the x-axis is assumed to be the coordinate which is parallel to the axis of the shaft, coordinate axis that's parallel to the axis of the shaft. If that is the case, then regardless of what the direction of these applied loads are, whether there are loads or moments, you can have moments as well, whether they're loads or moments, regardless of that, or also axial load. In this case, I don't see any axial load, but that might be there too. Regardless of all of that, in a shaft like this, and whether it's static or dynamic, even that doesn't matter, you will have only one normal stress, and that will be parallel to the axis of the shaft. So if your shaft is like this, if your shaft is like that, and you apply a bending moment, say about the z-axis, the normal stress that is created is parallel to the axis of the shaft. mz, therefore, creates sigma x. If you apply a bending moment about the y-axis, so this is mz as well, does everybody understand how those moments bend? So if I do this, this would be like mz, this bends like this. If I do my, it bends towards you or towards me, depending on the. So these are in two different directions. But regardless, they both give you a normal stress in the x direction. There will be no stresses in the y, normal stresses in the y or z directions, regardless. The axial load that may be applied will also give you a normal stress in the x direction in this case. So don't come up with a sigma y or a sigma z or something like that in problems involving shafts. Of course, if you apply a torque in the x direction, it will create a shear stress in the shaft. So if I pick any point on the surface of the shaft or any other part of the shaft, doesn't have to be on the surface, I will be confronted with this. One normal stress, one shear stress, regardless of the applied loads. Any questions? shafts are usually made of relatively ductile materials, only to make sure that a catastrophic failure does not occur. Only to make sure that if something is going wrong, or if the shaft is overloaded, and I'm not talking fatigue now because fatigue creates a brittle failure, but insofar as static loading is concerned, if the shaft is overloaded, it will either deflect so much that it can't do its function, or the slope will be such that the bearings will be misaligned and it starts to make noise and all of that, and you figure out there's something wrong, you go fix it. That, of course, is not true if we're talking about fatigue. That is something that you need to be aware of and check the part frequently to make sure that undue cracks are not present in it. But that's what shafts are made of. So I just talked about slope and the deflection of shafts. Let me ask you this question. Let's say we have two beams. Identical in dimensions, and they're both made of steel. However, this is a high-strength steel, let's say SUT equals 150 KSI. That's a ductile steel, SUT equals 80 KSI. Which one deflects more under that load? The one on the right or the one on the left? Does everyone agree? Yes? Let me change the problem a little bit. Same two beams, if you will. These two forces, of course, are equal. Which one elongates more? The one on the right? The left one. Well, you remember the equation for that? PL over AE, that's right. P is the same, L is the same, A is the same, E is the same. Never mind that the strengths are not the same. Strength has nothing to do with deflection or slope. FL over AE here. For this, delta max in the middle of the beam is FL cubed over 48 EI, if I remember correctly. I hope that's right. There's no strength in those two equations. It's immaterial what the strength is. The deformation of the shaft, or any other body for that matter, from a materials point of view, only a materials point of view, if I change the length, of course, it's a different ballgame, or the diameter, is solely a function of the stiffness of the material, from a materials point of view. And that's the only material constant you have here. And that's the same for steels, regardless of their strengths. Therefore, the answer to both of those is the same. Okay? Any questions? All right, let's take a break, then I'll continue when you come back. You have bending moments in two directions, and you've done this before in 219. And you know that what you need to do is draw shear moment diagrams one in the xz plane and the other one in the yz plane. Well, actually, they got them x, y, and xz, because x is their axis along the shaft. And you get two moment equations, and notice that if your moment equations are linear, such as these two are, then you have 2 points in here of relatively high moment. You have 2 points here of relatively high moment. In this case, it's obvious that the maximum moment occurs here because this is larger than that one and that's larger than this one. So it's no big deal. But if it were the other way around and this here was larger, then you would combine that with this one vectorially, combine this one with the other one vectorially. That would be the total bending moment. Whichever of those two is larger would be the one that you would use to calculate the stresses. In here, we were talking about deflection. If I double the diameter, what happens to the deflection? It goes down for sure. Yes, that's true. That's true. It'll go down. No question about that. But by what factor? Factor of 2, 4, 8, 16. What you should notice, this is for bending only, not that. It's related to I, right? And that's I for a circular cross section. It's dependent on the fourth power of the diameter. So if you double it, then it's 2 to the power of 4. That's how much the deflection decreases. By a 2 to the power of 4, 16. So a 1-inch deflection becomes 1/16 of an inch deflection, basically, by doing that. So that's one thing I wanted to mention. Your book actually has a little equation telling you if you want to change diameter and control deflection, a very simple equation. Another thing that I wanted to talk about is this. You have all drawn shear moment diagrams for beams or shafts. And those are the bottom two diagrams on the screen for each of those two loadings. But what I wanted to go to do and show you a little bit further is that the same relationship that exists between shear and moment exists between moment and slope and deflection. For example, we say that the slope of the moment diagram is equal to the magnitude of the shear force. That's a constant here, so that's a constant there. It's higher here, so the slope is higher there. The slope of the moment diagram is equal to, sorry, the magnitude of the moment is equal to the slope of the slope diagram. Slope of the slope diagram, yes. And that one I'm not mistaken. And the magnitude of the slope is equal to the slope of the deflection diagram. You've actually done all of these without saying as much. Remember this equation that from when you did it singular? I think you did it when singularity function in 219 or without singularity function. You said W is equal to the fourth derivative of the deflection. Remember that? You started from the load, not from the moment. You can start from the moment, but you started from the load. And he said we integrate this. W is a distributed load, by the way. We integrate this once, we get the shear force. Therefore, this is the derivative of that. So the magnitude of that is the slope of this. Take a look. There is no distributed load here. Therefore, the slope of the shear diagram is 0. No distributed load. W is 0. Not point load, distributed load. So, and then you said the moment is equal, there's an EI in here times EI. Times EI? Yeah, times EI. Then you had that. A lot of time you started with this. Said y double prime equals m over EI. So this, sorry, the shear force is the slope of the moment diagram. And, no. One more. Skipped slope here. Slope is equal to, what do they call it over? Theta is equal to y prime. Then you go one step further and you get deflection equals y. Integrate that, you get this. Integrate that, you get this. Integrate that, you get this. Integrate this, you get that. So you can say this is the slope of this one, that's the slope of this one. Exact relationship that exists between any two of these adjacent to one another can be transferred through the whole thing. So you can actually draw these diagrams without writing any equation, so long as you can calculate, for example, area under that diagram, because that'll be the change in the value, in this case, of the deflection. Any questions? So that's another point that I wanted to come up with. We need to look at the stresses in shafts from 2 points of view. One, static point of view, which we've done a lot of, and I'll rewrite the equations. And two, fatigue, which we've also done, and some of the equations that I will be writing you'll be familiar with. But we will make them much more general, much more complete. And in many cases, many of the values that you will see in these equations will be 0, which is fine, nothing wrong with it. So we said that a shaft, and by the way, all of these equations are in your book. If you want to just jot down stuff next to the equations in the book, that's fine. Or if you want to copy the equations that I write, that's also okay. I'm not going to write all of the equations because they're very long and drawn out, and there's no reason to do that. But I will write some sample equations so we can discuss them. If we have a shaft, it can be subjected to a bending moment, an axial load, and a torque. The bending moment and the axial load combined will produce a normal stress. And that normal stress is in the direction of the axis of the shaft. The torque produces a shear stress. Therefore, and this is all for solid shafts. So sigma is equal to 32m divided by pi d cubed plus 4f divided by pi d squared. Bending stress, the first expression. Axial stress, the second expression. There will also be a shear stress. I want to emphasize that in the direction of axis of the shaft. The shear stress will be equal to 16T divided by pi d cubed. And then we said we can analyze this. In other words, once again, this is our case. We can analyze this, assuming it's a ductile material, either by the maximum shear stress theory or by von Mises' maximum distortion energy. So for the maximum shear stress theory, we say yielding will occur when the maximum shear stress in the material at any point in the material reaches that at yield in simple tension test. So the maximum shear stress here, tau max, is equal to the square root of sigma over 2 squared plus tau squared for this. Is this the maximum in-plane shear stress or the maximum of all shear stresses or both or neither? Do you know where this comes from? Both. Comes from where? This equation? Mohr circle. That's right. That's right. And if you are going to have one normal stress and one shear stress, there's no choice. One of your principal stresses will be positive and the other one will be negative. And it doesn't matter whether this stress is tensile or compressive. For a compressive stress, it'll look like this. In both of these cases, the middle principal stress is 0. Therefore, what you find here is the maximum shear stress, the radius of the largest Mohr circle. And if we now substitute into this equation those values, we get this. We get 2 over pi d cubed times 8m plus fd squared plus 8t squared to the 1/2. We can also use the von Mises theory, or maximum distortion energy. Sigma prime will be equal to sigma squared plus 3 tau squared to the 1/2. Again, this is a shorthand notation of the von Mises equation, where you only have one shear stress and one normal stress, and that's what we have. Substituting those values, this is what you get. 4 over pi d cubed times 8m plus fd squared plus 48 t squared to the 1/2. And then you say, okay, factor of safety, n, is equal to Sy over 2 divided by tau max for the maximum shear stress theory. There's tau max, Sy for the material. And for the maximum distortion energy, the factor of safety is Sy over sigma prime. Now, the reason why we do all of this is that when you look at those two equations, the right-hand side of these two equations, this part here and that part there, you see no stresses. You only see forces, bending moments, and torques. Meaning that if you use these equations, you don't have to find the stresses and go draw more circle or do whatever. The only thing you have to do correctly, and that's why it's so important, and I emphasize it as much as I do, is statics. You have to find the moments, the torques, and the applied loads correctly. Otherwise, not only does this not work, even if you do this, it won't work. So that's why we do this. And you will see that throughout the equations that I will be writing in the book, which are not the complete set of equations in the book, but I will write some of them. Any questions? In many instances, the axial stress that is generated in the shaft is much, much smaller than the bending stress. So this is generally much, much smaller than that. So many times we neglect the axial stress and we just bring in the bending stress. If we do that, then these equations become tau max equals 16 over pi d cubed times m squared plus t squared to the 1/2. Sigma prime equals 16 over pi d cubed times 4m squared plus 3t squared to the 1/2. So as soon as you find the moment and the torque, you can find the critical stresses very easily. One word of caution, because I have seen this generally in industry, where people are trying to simply apply equations without thinking sometimes. Even though this looks like we're combining these two, a squared plus b squared, you take the square root of, vectorial addition, and that is what we're doing. But that's not where it came from. It came from the stresses. But it looks like that anyway. You shouldn't combine the normal stress and the shear stress in this fashion. Moment and torque, you can do that, they're vectors. Stresses are not vectors. You cannot combine them vectorially. So even though this looks like that, and it is a correct equation, no question about that, make sure that you understand that it doesn't come from adding stresses vectorially. Number one. Number two, I've seen some people do this. Say, okay, so we have this. All right, and look at this. This looks like a 16t divided by pi d cubed. Or if you want the moment equation, you can write that, and it'll be something very similar to this. What I've seen done in industry is they take this, and there's only a moment and a torque in the shaft, nothing else. You take that, and they say, okay, that's my moment, which is okay. That is a moment. And then they use this. Can't be doing that. You already got a torque in here. That's not the equation for stress and torque. So don't do that. Yes, it's a combination of those two, but that's basically where we stop. If we want to find either the factor of safety or the diameter of the shaft, given some factor of safety. We can convert these equations to equations that give you the diameter and the factor of safety. And let me write those equations for these two. These are the simpler forms of the equations that we will take a look at. For the maximum shear stress theory, we get D equals 32 ND. ND is the design factor divided by pi SY. Your book may or may not have the subscript D on it, and whether you want to use it or not, it really doesn't matter. And 1 over n equals 32 divided by pi d cubed sy times m squared plus t squared to the 1/2. That's the design factor. This is the factor of safety. There is a difference between the two. The design factor is the factor with which you start your design. You say, for example, for the design factor of 2, find the diameter. So you find the diameter. Find this. Design factor 2, you find that diameter. And it comes out to be 1.289. Well, 1.289 is no diameter that you can find in the market, so you go up to the next higher size. As you do so, the original design factor, which was 2, has now been increased to 2.2, 2.5, whatever. That's this factor of safety. That's the difference between the two. And the design factor is less than or equal to the factor of safety. A similar set of equations for MDE. D equals 16n divided by pi sy times 4m squared plus 3t squared to the 1/2 to the 1/3, like so. Did I have that bracket? I need this bracket over here as well, like that. And 1 over n equals 16 divided by pi d cubed sy 4m squared plus 3t squared to the 1/2. These are the static design equations for the diameter and also factor of safety. Now, that is if you have no varying loads. In most cases, that of course is not true. And we have shafts rotating and or moments and torques varying. So in general, what we will do is say we will assume that the bending moment changes and not necessarily completely reversed, which is the case in most shafts, but not necessarily. We'll look at a general equation. The torque will also fluctuate, so each one will have a mean value and an alternating value. If that's the case, we would like to see how to deal with the failure of the shaft in fatigue. So, very similar to what we have done. Failure locus, a failure criterion, and I'll use Gerber now to show you how they find these equations, at least for that one. And then I won't go through the details for the other ones. And now we also plot our point. That'll be our load line. These are our limiting values. The question now is, how do we find the coordinates of that point? The point to be plotted. Remember when we did combined loading for fatigue? We said for each one of these applied loads, meaning moment and torque, for the time being we will disregard the axial load. That can be included as well. But just the torque and the moment. We find an alternating value, we find a mean value. For each of those, we find a von Mises stress. Alternating von Mises, mean von Mises. Based on the equations, you can do these equations or the ones that I had on before, but this is what we have. So sigma A prime, the alternating von Mises stress, is equal to sigma A squared plus 3 tau A squared. And each of these comes from the alternating value of the moment or torque respectively, to the 1/2. And if we substitute for these values, we did this for static loading. We did this for combined fatigue, so this should be familiar. This is similar to the equation that I had on the board, 16 over pi d cubed, the one that I got those two from. This is what we get. The square root of 4 kf ma squared plus 3 kfs ta squared. This is exactly the same equation as before. 16 divided by pi d cubed, 4 m squared, 3 t squared. The only thing that's been added here is kfs and kf. These are stress concentration factors, fatigue stress concentration factors. One for bending, one for torsion. Remember that it doesn't matter if you multiply the stress by that or the moment. And sigma m prime is equal to sigma m squared plus 3 tau m squared to the 1/2. That gives you 16 divided by pi d cubed times the square root of 4 times kf mm squared plus 3 times kfs tm squared. We'll call this 16a divided by pi d cubed. We'll call that 16b divided by pi d cubed, where b is this radical, a is that one. These are my two stresses, alternating and mean. What's the slope of the load line? A over B, that's right. Slope of the load line is A over B. Immediately you can draw the load line. Notice no calculation of stress is necessary. It's all dependent on the applied loads, bending moments, and all of that. And now we can do exactly the same thing as we did before. Find the coordinates of that point called SM and SA. Write the equation for the Gerber line. That's a Gerber line is a parabola Its equation looks like this. Oops. SA over SE plus SM over SUT squared equals 1. That's the equation of the Gerber line. The equation of the load line, of course, is SA equals A over B SM. You solve those two equations, and both of these, of course, are written for this point. That point must satisfy the equations of both lines, both the Gerber line and the load line. We solve these two, we find the value of SM and divide it by sigma A prime, sigma M prime to get the factor of safety, or SA. A simpler way would be to say the factor of safety is the factor by which I can multiply this length before I get there. So if I multiply these two, sigma A prime and sigma M prime, by the factor of safety, it must give me that. So here's what I do. That's the Gerber line right here. So I'll go in here and say N sigma A prime over SE instead of sigma A plus N sigma M prime over SUT squared equals 1, and solve for N. If we do that, we will get two equations, one for the factor of safety and one for the diameter, depending on whether you're doing analysis or design. And those equations look like this. D will be equal to 8 NDA. Again, your book may not have that subscript D. I just want to do that to separate it from the factor of safety. 1 plus 2B SE divided by A SUT squared to the 1/2 to the 1/3. And A and B as defined before. 1 over n, this is not a factor of safety. 8a divided by pi d cubed SE times 1 plus one plus 1 plus 2BSE divided by ASUT squared to the 1/2. Now, these equations are called D.E. Gerber, meaning we calculated the stresses using the distortion energy or von Mises equation. We used the Gerber failure criterion. There are others, such as, for example, ASME. You will see dE ASME. The only difference is that that goes from SE to SY. This is ASME, and that's Gerber. And the ASME is ellipse, so you see it as dE elliptic. And the equations for dE elliptic are also in the book. What page are they on? Whoever has the book open?
361.
361. Yeah, all of the equations are page 360 and 361. One special case I want to write, because it occurs most often. And that is when you have a completely reversed normal stress. In other words, the bending moment is constant, the shaft is rotating. Completely reversed bending stress. And the torque that's being transmitted is a constant. So if that's what we have, for completely reversed bending and steady torsion, we will have these equations. Oh, actually, they're so long and drawn out, I'd rather not write them. I'll just refer you to them. They are equations. I'll write what they entail, but they are equations. This would be for the dE elliptic. Oh, they don't have equations similar to the ones that I have. Well, I'll write them on the board. It will take some time, but I will write them on the board. D equals 16N KF, that's the stress concentration factor, fatigue, MA divided by pi SE times 1 plus 1 plus 3 KFS TM SE divided by KF MA SUT. This is your A over B, slope of the line, squared to the 1/2 and to the 1/3. Notice that the only thing you need here is alternating moment, mean moment, alternating torque, mean torque. And the mean torque and the alternating torque, TA, and the mean moment are 0. Same equations. This is for dE elliptic. So 1 over n then is equal to 16 KF MA divided by pi d cubed SE times 1 plus 3 KF TM SE divided by KF MA SUT squared to the 1/2. And you see that the two equations are actually one equation. To get the lower equation from the upper equation, you solve for n. That's what you get. That's all. And in the other one, you solve for d cubed. That's why you get the 1/3. So these are the equations, and all of these equations, including that for Gerber. This is for including that for Goodman. This is the equation for the Gerber criterion. The ASME, the elliptic is also there. One sign, of course, is if you see that and it's a nonlinear equation, it's probably Gerber. If you see this and it's a nonlinear equation, it's ASME. Now you might say, well, we could use a linear equation too. Yes, you can, but the linear equation comparable to ASME would be this. This is the Soderberg. The problem there is that you will be missing all of these areas. The ASME, the elliptic is used extensively in industry. It's the actual equation that's used a lot in industry for fatigue analysis. Any questions? Okay, one last part here remains that is basically not stress analysis, but control of, by the way, if any of these comes up in the exam, of course, you're free to use the equations as you wish. Only the linear equations will I ask you to write out the equation and actually solve them together. They're very simplest forms. Not any of these, of course. But when a shaft carries a load, even if when it doesn't carry an externally applied load and it's under its own weight, and it rotates, it will have a tendency, due to the speed of the rotation, to deflect. And that deflection changes, and it does this, a type of vibration called whirling. And in whirling, what happens is that the deflection of the shaft keeps increasing to a point where the shaft fails, basically breaks. We would like to avoid that. Each body is associated with what is called a natural frequency. Shaft, no exception. It has a natural frequency due to its own weight. And we must make sure that the natural frequency of the shaft and the frequency of the applied load, that's frequency of applied load would be the frequency of rotation, never get close to one another. In fact, we would like the frequency of the shaft to be at least two times that of the externally applied load. And in order to do that, we find the natural frequency of the shaft using a vibration equation. And even if you've not taken vibration, you're probably familiar with this. That equation looks like this. Omega is equal to pi over L squared, square root of EI over M, equal to pi over L squared times GEI divided by A gamma to the 1/2. In these equations, L is the length of the shaft. M is mass per unit length. And this part of the equation would be convenient in the metric system, where you usually have mass. This one would be convenient for the US customary system. In this one, A, the cross-sectional area of the shaft, and gamma is the specific weight. G is the acceleration of gravity. So we calculate this. We know the frequency of the applied load. We make sure this is at least twice that to make sure that the shaft doesn't vibrate out of hand. And you can, of course, as you can see, for example, you can decrease the mass, increase the mass, and change that, or I or E, all of those are possible. If there is a load on the shaft, and by the way, they usually calculate the frequency like that. Divide the weight of the shaft into little pieces and apply each of them at a point. But if there are actual loads applied, there's none here, but if there's actual load applied, like a gear or a sprocket or something like that, then those will have weight at whatever points, and then we use this equation to find the natural frequency. Omega would be equal to the square root of G times the summation of Wi yi divided by the summation of Wi yi squared. In this case, Wi is the weight at ith point, yi deflection at ith point due to all loads. You find that frequency and you make sure that it is at least twice that of the externally applied load, the frequency of the externally applied load. Any questions? Okay. One reminder, Tuesday you will have your exam. As I mentioned in my email, it will be similar to the last exam, and we'll have 10 multiple choice questions worth 10 points and 2 problems, totally worth 30 points. Whether the points will be equally divided or not, I don't know yet. But 30 points for the 2 problems, 10 points for the questions. Questions constitute a quarter of the exam. You will have 75 minutes, and we'll do exactly the same thing we did before. Let's see. The questions for the general fatigue problem could include a shaft such as this. And if you're to use these equations, I'll refer you to these equations. And you can use them straight out. Or if you are asked to draw a Goodman line or a Soderberg line, write the equations and actually show how you get the values, then that's kosher as well. Okay. Also, I will be here tomorrow. I will have office hours from 9:45 to 10:45 if you would like to see me. I may or may not have office hours on Monday. I don't know. If I do have office hours on Monday, I will send you an email to that effect. Okay? Any questions? All right. Have a good weekend. I'll see you on Tuesday.